So, me and Nick has been dating for 5 years now, and he was always so nice to me. He got me ice cream, he always gets me my favorite food. Oh, and I remember last year, he got me a cassette tape. But how does he know I like it though? I've never told him before. Maybe he just knows me that well. And he always cuddles me in the common room on our favorite sofa. And every time when I'm down, he always cares for me and then cuddles me and tells me that everything's gonna be alright. But recently, he's changed. I just feel like he's kind of cold to me now. Like he's not with me anymore, you know? Like he doesn't love me. Does he love me? Sometimes I just feel like our love is like two parallel train tracks in a painting. Like they seem to come together, but then in reality, they just don't actually meet, you know?
Let's stop right there. Justin seems to be struggling with his relationship with Nick. For those out there who know me, to be honest, I'm probably the last person you want to ask about relationship advice. However, as a mathematician, what I can do is solve math problems. And if you make love a math problem, then I can certainly solve that for you. What Justin does here conveniently for us is he compares his love to two parallel train tracks that he doesn't know if they will meet or not, or if they will simply run parallel. That, however, I can solve using my knowledge of linear equations. But how do we solve linear equations? Let's find out today.
So hey guys, today we've got mathematician Mr. Alex Arnold here, so would you like to introduce yourself?
Hello, I'm Alexander Arnold. I'm a mathematician with the University of Lancaster.
Yeah, so how do you actually model math in real life?
Well, I think that, to be honest, mathematics can be modeled from any sort of application in real life. You know, I mean, let's just get started. I think it's everywhere in this school and we can find it right now.
And I think that already one of the most obvious places in which you can see an application of mathematics is already in the bathroom. You see, these toilet bowls are sort of in an elliptical shape, and we have equations. Thank you. We have equations in conics that can be used to actually model the shape of these toilet seats, and that definitely facilitates the production of these toilet seats.
I think that another application you can see right here, you know, if we compare the number of steps we've walked from the bottom with how high we've gone from the bottom, because every single stair is the same height, we then begin to see some sort of like linear progression in the way that we've been walking up the stairs. And I think that already that's another very significant application of mathematics that we found within this building. And now we're here in this art gallery, and as you can see, there's lots of art around us. But the thing is, we can even model art using mathematics. Let's take a look at this painting over here. It's quite a rich painting. You can see this sort of like wallpapery stuff on this red background, and to be honest, this cannot be modeled using math. I have no clue how we would actually model this using math. But this, however, I think we can analyze. Let's go break it down. So we have the piece of artwork here from earlier, right? And I think that we see these two train tracks here, yet we don't know if they are going to converge or not, right? So I think what we can do here then is we can use our knowledge of linear mathematics to be able to show whether or not these things will converge by modeling them. How do we do that? What we need to do first then is we need to identify our reference frame, you know, the sort of space that we're working with, right? Let's identify the length, so down here to be the x-axis, right? And then, or well, presumably into the distance here, right? And then the width, right, across the tracks to be our y-axis. What we have here now is we have these two lines, these tracks that we want to sort of identify the equation for, right? Given our knowledge of train tracks, though, we know that they're straight, so we know they represent linear functions, which is this straight line, and only because of the perspective of the art do they appear to converge like this, right? Yeah. So I think that because we know that this is x, this is considered to be x equals 0, as the sort of like line going down the middle, and this is y equals 0, we know that this equation is going to be, since there's probably roughly, I don't know, like a distance between the tracks of maybe 0.5 meters. We know that this one will be equal to x equals negative 0.5, and the one on the right side will be equal to x equals to 0.5 positive, correct?
Yeah.
That makes sense, right? And what we can do then is we can use our knowledge to see if two lines like this are parallel or if they converge. So a space, an equation, and a solution. I think that you can see that already in this room, right?
Really?
What we have is a space. What is the space we live in? We live in a three-dimensional space. That means that we have x, which is the length, we have y, which is the width, and then we have z, which is the height. This represents the three different directions in which you can go on the world we live in. That shows that we live in a space that is three-dimensional, right? What that means then is if you wanted to find something and use like maybe vectors to solve something within this space, what you have to do then is you have equations. You have maybe sort of like planes or lines that go through this space that are represented using those x, y, and z's that I've just spoken about and the relationships in between them. This will become a bit more apparent later. But finally, we have solutions, right?
Yeah.
Solutions are the points or possibly lines or even planes at which these these equations that we're using become resolved, at which most likely they meet. This will too become a bit more apparent later.
Okay.
But now that we understand what a space, an equation, and a solution is, what we need to do is we need to look at these in the different possible ways that they can show up. Here's what I mean. Let's start with a one-dimensional space. A one-dimensional space is represented as a line. The solution of that one-dimensional space, then, is simply a point along the line, right? And we can often resolve these using basic algebra. 3x plus 1 is equal to 0, x is equal to negative 1 over 3. Something as simple as that. Along this line is the point where x is equal to negative 1 over 3. That's our solution. Let's move into a more complicated space then, a two-dimensional space, where we have an x and we have a y. Okay? What we have then is we have two lines represented by whatever y equals mx plus b is, and they intersect at a certain point. And that point is where the solution is. But let's push it even further, right? Let's move into a three-dimensional space, right? In a three-dimensional space, equations are represented by two-dimensional planes.
Yeah.
If you look back to the two-dimensional space, equations are represented by one-dimensional lines. Now we go into our three-dimensional space, we have an x, y, and z, we put these planes together, and when we put two planes together, what's our solution? Our solution is this line along the middle. It's this line, it's a two-dimensional representation. Now we take in a third equation, a third plane in this three-dimensional space, and then we intersect it. It's a little hard to see, to be honest, but in reality, what's happening is it's intersecting at a point. And this point is the solution, thereby showing that what you have is you've gone from a three-dimensional space, two-dimensional planes, with two equations, you bring yourself to a one-dimensional solution, and then when you put three planes together, you get a zero-dimensional point as a solution.
Okay, so now that we actually understand how these linear equations work, how they work in all of their dimensions, let's hear from Kevin on how to actually solve these linear equations.
So I will talk about how to solve two simultaneous equations by elimination. So firstly, this is equation 1, that's ax plus by equals c. So as you can see, a and b are the coefficients in this equation, and x and y are the variables. And then we have equation 2, 3ax minus by equals d. So what's the elimination method means? It means that you either add or subtract the equation to get an equation in one variable, so which can help us to get the answer. Because you see, we have plus by and then minus by. So we can actually add these two equations together. Then we only need to consider about x because we don't have any y in these two equations. So let's try an example question. First equation is 4x plus 7y equals 16. Then 3x plus 21y equals 21. As I wrote here, firstly, we want only one variable in these two equations. So we multiply 3 for the equation 1, which is 12x plus 21y equals 48. Then we wanted to keep only one variable, so we can delete equation 1 to the equation 2. So for each step, there have to be a subtraction. Now we can get the answer. 9x equals to 27. That's the answer. When we know that x equals to 3, we can put the value of x back to the equation. So whether equation 1 or equation 2. So firstly, maybe equation 1, that's 12 plus 7y equals 16. So 7y equals to 4, and y equals to 4 over 7. So that's the way, just like how to use elimination method to solve two simultaneous equations.
Okay, so solving simultaneous equations with 3 unknowns. Well, how do we do that? Well, it's actually really similar to solving the ones with only 2 unknowns, where you essentially try to eliminate variables until you have only 1 unknown left. So let's say we have the example x plus y minus z equals to 0, 2x minus 3y plus z equals to 1, and 2x plus y plus 2z equals to 7. So what we do first is we can pick 2 equations. So let's say we choose to minus the second equation from the third equation. So after you minus it, you'll be left over the equation 4y plus z equals 6. So we can do the same thing with another 2 equations. And let's say, we pick the first and the second equation. Well, we can clearly see that in this case, the x coefficients are different. But then what we can do is we can manipulate the first equation by multiplying both sides by 2, so that the x term of both equations will be 2. And after that, we'll get 2 equations that has the same coefficient of 2 for the x term. And in this case, we can do the same thing again by minusing the first equation by the third equation. And after that, you'll be left off with the equation negative y plus 4z equals to 7. And so after the first and the third step, we have 2 equations with only 2 unknowns. Well, in this case, it will essentially be the same process as solving simultaneous equations with 2 unknowns, where again, we can do the same process of elimination, where we try to get the coefficients of a certain term to be the same. And in this case, we can multiply the second equation by 4 on both sides. We'll get the equation 16y plus 4z equals to 24. And in this case, we can do elimination process again, where we minus the second equation, we minus the first equation from the second equation. And after subtraction, we're able to solve for y, where 17y equals to 17 and y equals to 1. And after we get the value for y, we'll be able to substitute it back into our 2 equations, where let's say we substitute it into 16y plus 4z equals to 24. So 16 times 1 is 16 plus 4z equals to 24. So you'll be able to get the final value of z equals to 2. So after you get the values of y and z, we can substitute it back into the very original equation, x plus y minus z equals to 0, which is the first equation we've talked about. And after substituting in, we'll get to x plus y minus 2 equals to 0, where we get to the final value of x equals to 1. So that's essentially how you solve simultaneous equations with 3 unknowns, where it's really similar to the one with 2.
And that, Justin, is how you solve simultaneous equations.
Well then, all I really want to know is, does Nick actually love me?
That's what you wanted to know? Well, why don't you just go ask him yourself?
Yeah, maybe he's right. Probably go ask him. Nick, do you love me?
Of course I do.